All right, hi everyone. Today we'll be doing the next topic for exponential and logarithmic functions, and that's going to be on properties of exponential functions. Now, before we head to that, let's work on this. Some problems here. I got two problems here for the bell work technically. All right, so here it says write an exponential function to model each situation and then also find the amount after the specified time. So if you would see here, this first question here says a population of 120,000 grows 1.2% per year for 15 years. So since it says here the word grows, so we know it's an exponential growth. So if we are going to find the future value, so our setup would be our initial value, which is 120,000. And then we multiply that with 1 plus our percent, which is 1.2%. If we change it to decimal, it's going to be 0.012. And the number of years will serve as our exponent, and that's going to be 15. And so when you hit that on your calculators, you will be able to get the population of, let me see here, 143,000. So here we're talking about population, so we are going to round it up to the nearest whole number because we're talking about population, all right? So our population will end up to be 143,512. Okay, so that's the population that is expected after 15 years. For the next example, here, as you can see, the word is decreases, so we know it's going to be a decay. Now, similarly, we can set it up like this. So we have our initial value, which is 1,860,000. Now, as you can see, it is a decrease, which means instead of addition, this is going to be 1 minus 1.5% is now going to be 0.015. And in this case, it's good for 12 years. So we write our 12 years up here. And if you use your calculator, again, we're talking about populations, it's going to be a whole number. This is going to be 1,551,485. So again, from 1,860 in 12 years, it's going to go down to 1,551,485. All right, so that's a quick review of our previous topic. And so as I was mentioning earlier, we're going to go ahead with the properties of exponential functions. This is not going to be a tough topic because the properties that we will be talking about here are the transformations. And then also, I would like to introduce you to what we call as our natural exponential with the base e. Okay, so let's proceed. So with the exponential function family, our parent function, as you can see, will be written as y is equal to b, which is any number, raised to x. All right. So anytime we see symbols, numbers attached to this parent function, it corresponds to a transformation. And we have gone over different transformation rules from the previous functions that we've had. So as you can see, I tried to color code it. If you see a negative sign, okay, that is when it will ask you to reflect the functions, the graph. If you have a multiplier, so that's the letter A, that's another number over here. That multiplier could either stretch or compress depending on the value of this number. So if that multiplier is greater than 1, then it's a stretch. If not greater than 1, then it's going to be a compress. And then of course, if we see some addition, subtraction happening in this function, so that would correspond to translation. So if you are adding or subtracting together with x in the exponent, that corresponds to the horizontal movement. So if it is a plus h, it's moving to the left. If it's a minus h, it's going to move to the right. Last but not the least, addition or subtraction at the end, as you can see, it stands by itself. So this is your vertical translation. So positive k is going up, minus k is going to be going down. So let's have some comparison of the parent function to this upcoming functions here. So again, it should just be a number raised to x. So any other symbols, they correspond to transformation. And if we look, so you can start looking from left to right. So the very first thing we see is this negative. So what do we have there? We know that there's going to be a reflection. Okay, then we also have this multiplier. Our multiplier is 1/3. And from our notes, 1/3 is less than 1. It's between 0 and 1. And so this means that there will also be a compression. So the function will be compressed. Okay, for this next example, we do not have any negatives or multipliers here. We already have the base b. But if we notice, we have a number subtracted with the exponent x. So this means that there is a movement going to the right by 4. 4 units going to the right. Okay. Last example here. So as we can see, again, we start from the left. Negatives, none. Do we have a multiplier? Yes, this multiplier 20 is very much higher than 1. So we know it's going to be a stretch for our function. We do not have anything added or subtracted to our x exponent, so no horizontal movement, but we do have some vertical movements, and this as plus 10 means simply that we are going to go up by 10 units. All right. So pretty much that's everything for transformations of functions, of exponential functions, I must say. Okay, so we have what we call as the natural base exponential function. So normal exponential functions, you have a number, okay? So let's say 2 raised to the power of x, okay? This is always a number. The base is always a number. Now, there's a special case which we call as the natural base. In this scenario, the base instead of the number is actually the number e, okay? E, just like pi, has a numeric value, okay? So we use the natural base exponential function if we are describing continuous growth or decay. So let's try out using our base e on our calculator. So let's find the value of e raised to the third power. Now, for you to locate the e on your calculator, you gotta look at the number 7 and 4. It's to the left of it. And as you can see, E is colored blue. So you have to hit the button second first before you press the LN button. This is LN, all right? So if you do your calculation, E raised to the third power, that's going to be equal to, if we do 2 decimal places, this is going to be equal to 20.09. All right. One more example, e raised to the 8th power. You hit that on your calculators, and this is now going to be 2,980.96. All right. So as we have mentioned from the description of natural base exponential, we use this for continuous growth or decay. Now, last time we were talking about investing, saving money. Now, there is also another way on, this is another way of growing your money faster. And if you apply or if you use continuous compounding of your interest, okay? So now the formula, okay, last time, when we had the investment formula, it was initial value times 1 plus the R raised to the time, okay? So this is the normal savings, save getting interest every year. Now, if you see in the word problem, similar to this, okay, that it mentions the word continuously, then this is going to be the formula that you will be using. So P is still the principal, or what we call as the initial value. That's our E. And then our R and T are now both exponents. So R times the number of years will be in the exponent. So let's have this example. So let's say we have a deposit of $3,000 that pays 5% annual interest. There we go. Compounded continuously. Okay. So you got to be mindful reading those problems. Okay. So you know which is the appropriate formula to use. So how much will you have in the account after 4 years? So again, it was mentioned that it is a continuous compounding. Therefore, we are going to use the PERT formula. So replacing our values, our initial value is 3,000. Okay. We use the E. Now our R, oops, sorry about that. Our R now is, as you can see, it says 5%. So the exponent here will be 0.05. And it still needs to be multiplied to the t, which is 4 years. Okay? And if you do your calculations, you will get that the amount of money in the account will then become 3,664 and 21 cents. Okay, so this is because it is a continuous growth of the money. Now let's compare it with the normal. Let's say the problem did not say it's compounded continuously, and let's compare which one will give us a higher amount of money. So if we use the old formula, and again, let me just switch a different color. So this is if it was a normal annual interest, okay? So if that was the case, we would have 3,000 times 1 plus our percent, which is 0.05, raised to the fourth power. And if you do your calculations for that, you will notice that this amount is going to be 3,646 and 52 cents. Okay, so as you can see, the word continuous compounding really matters, because if you take a look, it's the same number of years, it's the same rate, but because of the presence of the word continuous compounding, it is a continuous growth, and you would see there's a big difference between the growth, the grown money into the account. All right, thank you so much.